Welcome to this lecture. Let's quickly recall what we have done in the previous lecture. So in the previous lecture we motivated the need for the analysis of functions that are defined on the sample spaces, or more generally, if you have a non-empty set together with some appropriate sigma field which constitutes a measurable space, we are looking at functions out of those, and we want to look at these numerical features which gives us some nice ideas about the underlying measurable space. So specifically, when you are dealing with a random experiment and looking at the sample space together with the collection of events, so that is one measurable space, then you are looking at all these outcomes that come out or appear as part of the random experiment, and you are interested in these numerical values. So this is why we started looking at these functions that appear or are defined on the domain space omega. So then with this in hand, we then looked at the type of conditions that we want to discuss, and we called it measurability conditions, and we defined something called measurable functions. So what was measurable functions? So if you take a function from omega 1 to omega 2, then first fix appropriate sigma fields on the domain omega 1 and the range omega 2. Then with those sigma fields at hand, you first look at the sets coming from the range side sigma field. So those sets which are coming from the range side sigma field, you take those and look at their pre-images. If their pre-images fall in the domain side sigma field, you will call the function to be measurable with respect to those two specific sigma fields. So the idea was that if you change the sigma fields, then you might get different measurable functions. So in particular, we chose to look at the range when it was the real line, and we defined the class of functions called Borel measurable functions. So on the real line, we are working with the Borel sigma field, and we had mentioned that if the sigma fields are understood, or at the beginning of certain discussions, if you fix those sigma fields and do not change them anywhere, then you can drop those for the simplicity of notations and simply say that the function is measurable. You don't have to explicitly mention the sigma fields as long as it is clear from the context. Okay. So that was what we had discussed last time, and at the end we had also looked at a couple of examples of these measurable functions. In particular, we talked about this large class of examples that appear from the continuous functions on R. Real valued continuous functions on R are Borel measurable functions. Okay, so that gives you a large class of examples to use. Alright, so with that at hand, we are now going to start the discussion in this lecture. So as usual, let's move on to the slides. So again, in the previous lecture we discussed the concept of real valued measurable functions, the Borel measurable functions. But in practice, you might need to work with functions which takes values in the vector space Rd, so which are vector valued functions. Or you might have to allow functions which take plus or minus infinity as their values. So you will have to work with the extended real number system. So therefore, if you just work with the real numbers or look at functions taking values in the set of real numbers, then this will not be enough for the applications that you might find in practice. So you have to devise, or you have to understand or discuss these functions which could take values in some higher dimensional Euclidean space or the extended real line. So we are now going to define the concept of Rd valued or R bar, the extended real valued measurable functions. So this will again follow the similar notions. All you have to do is to put the appropriate sigma fields on the range side, which are these Rd or the extended real line R bar. So recall that the Borel sigma fields for Rd and R bar were discussed earlier in week 1. So please check that discussion. We had already defined it. Now we can also consider taking functions which are taking values in r bar d, so d-fold product of the extended real line. But in this course we are not going to discuss such functions. We may consider this, but these are not going to be used in this course, so therefore we are going to ignore this specific type of functions. The understanding obtained from functions taking values in rd or the extended real line r bar is good enough for us. So with that clarification at hand, so let's look at this definition. So we are going to look at this rd valued or r bar valued measurable functions, and we are again going to call them as Borel measurable functions. So what are these? So take omega tilde to be either rd or r bar, the extended real line, and let omega f be the measurable space, so that is on your domain side. Omega f is given to you, so that is on the domain side. On the range side you are going to put omega tilde. So then you are looking at functions with domain omega and range omega tilde. So omega tilde has two possible choices, one is rd or r bar. Now you are going to call such a arbitrary function from omega to omega tilde to be Borel measurable if it is measurable with respect to these sigma fields. So on the domain side you are given the sigma field script f, and on the range side you have the Borel sigma field. So if you are having omega tilde as rd, you are going to put the Borel sigma field of rd on the range side. If you are having omega tilde as the extended real line r bar, you are going to put the Borel sigma field on the extended real line on the range side. So with these two appropriate sigma fields at hand, scripted f and the appropriate Borel sigma field, if you get the measurability of the function, then you are going to call it a Borel measurable function. Okay, so it will be clear from the context what type of functions you are taking and in what kind of spaces the function is taking values in. Okay, it could be real line, it could be rd, or it could be r bar. So a clarification is needed with this point. So for notational convenience, we are going to use this term Borel measurable to refer to functions which may take values in r or rd or r bar. But it will be clear from the context when you fix your function or start the discussion, you are going to talk about some specific type of functions, and then you will immediately specify the domain and the range. So to talk about a function, you have to first specify the domain and the range. So once you do that, it will be clear what space is on the range side. So it could be real line, it could be rd, it could be the extended real line r bar. So in all of these cases, if the measurability conditions are satisfied, if you get the function is measurable with respect to the appropriate sigma fields, then you are going to call it a Borel measurable function. This is simply for notational convenience. Okay, because all of these are in some sense related to the real line. So for all such functions, we are going to use the term Borel measurable. We are not going to restrict it to only the functions which will be taking values in the real line. But in practice, I might be working with only the functions which are taking values in the real line or rd or r bar. Okay. So here what we are doing is that we are combining this definition 2 that was made in the previous lecture for Borel measurable functions, real valued Borel measurable functions, and the definition 3 which we made now. Okay. So we have just combined it and we just call all such functions to be Borel measurable, and as explained that we are going to look at all such functions which are taking values in either the real line or rd or r bar, but again it will be clear from the context what is your range set. Alright. So now if you continue with the discussions earlier in your note 5, so here we had introduced some certain notations. So that notations were used for real valued Borel measurable functions. So now that we have decided to call functions also taking values in rd or r bar as Borel measurable functions, then what we are going to do is to use this notation again. So we are going to specify the appropriate sigma fields on the domain side, and we are going to specify the range together with the appropriate sigma field. So the function f a priori is just a function from omega to omega tilde, but we are putting the sigma fields in to specify its measurable structure, meaning to check the measurability of function small f, you will have to use this sigma field scripted f and the Borel sigma field on the range side. So this is the notation or the statement that will be used. Similarly, a shorthand notation we can use just to say that f from omega to omega tilde is Borel measurable as long as the sigma fields in question are clear. Okay, this is again for simplification of the notation. Okay, all right. But then another further simplification, once you are only restricting your attention to Borel measurable functions, just say that these are measurable functions. So if you are working with real valued functions, for example, then you can simply say they are measurable functions, and it will be clear from the context that you are using the Borel sigma field on the real line, and you don't have to specify Borel measurable, the term Borel measurable, and simply say that it's measurable. So this is again another simplification, but we will try to use the term Borel measurable instead of saying just measurable, but it can be used. Okay, but again, in all such discussions, sigma fields in question should be clearly stated. So this is very important. So with this terminology at hand, you can now ask what are the examples of Borel measurable functions when you are looking at the Rd or the R bar as the range space. And it so happens that the constant functions, as we have discussed in the previous lecture, will again turn out to be Borel measurable functions. So why? Because the pre-images for the constant function is either in the empty set or the whole set, and that's always in the domain side sigma field, no matter what sigma field you choose on the domain side. So with that at hand, you always get constant functions to be measurable. But then we explained or discussed this issue in the last lecture, that beyond the constant functions, we are interested in the non-constant measurable functions. So now we are looking at non-constant Borel measurable functions which might now take values in Rd or R bar. Okay, so with that we want to figure out examples of this. But now there are a large class of examples suggested by the exercise 3. Show that all real valued Borel measurable functions are extended real valued Borel measurable functions. So what is the meaning of this? So given a function on some domain omega with appropriate sigma fields, and with the range real line with the Borel sigma field on real line, if it is given to be measurable function, then you can now simply think of that function taking values in the extended real line, because the real line is contained in the extended real line. So you can as well think of all those functions as taking values in the extended real line. The function has domain omega and the function has range the extended real line. So I put the given sigma field on the domain side, but on the range side with the extended real line I put the Borel sigma field there, Borel sigma field of the extended real line. Now you can ask, okay, is this measurable with respect to the Borel sigma field of the extended real line? And the answer is yes, as suggested by exercise 3. So please work this out. Okay, so now this is a quite a interesting comment about principle of good sets. So remember, we had discussed this principle of good sets in a brief manner in note 22 of week 1. We said that this general principle that allows us to prove certain types of results. But we said that due to certain complexity of the arguments, we are not going into the actual details and we are going to use it as a fact, or whatever facts we can derive from the principle of good sets, we will take them as granted. So that's what we had mentioned in note 22. And using such a principle, what you can show is that you can prove the following statement. So take two measurable spaces omega 1 f1, omega 2 f2, and choose or obtain a class of sets for the range side sigma field. So here omega 1 is the domain, omega 2 is the range. So script f2 is the sigma field on the range side. So figure out a generating collection of sets for script f2. Call it script c. Okay. So then the statement says that the pre-images for sets coming from the smaller collection, the generating collection, take only those generating collections. So those sets, if you look at them, take those sets A and look at their pre-images. Then these pre-images, if they lie in the domain side sigma field, then it will be measurable. So remember, for the measurability, as per the definition, you are supposed to look at all possible sets coming from f2, the script f2. But we are saying that instead of looking at all possible sets coming from the script f2, we just choose to look at only the generating sets on the range side. Take only those sets A and look at their pre-images. If the pre-images fall in the domain side sigma field, then your function will be measurable. So this actually is a if and only if condition, so that it can be proved by the principle of good sets. Okay, so to check measurability, it's enough if you just check the measurability of f, these conditions for measurability only for the generating class of sets on the range side. And this observation can be used to prove the proposition 1 that was discussed in the previous lecture. So what was in proposition 1? We said that all functions from R to R which are continuous are Borel measurable. So there we had mentioned one exercise that pre-images of open sets are open. So if you put it together with this fact that we have just mentioned now, you can actually prove the proposition 1 and say that yes, all continuous functions from R to R are Borel measurable. Okay. We can also generalize proposition 1 to the following fact. So this is a statement in higher dimensions. So now we are saying take continuous functions from Rn to Rm. So n and m are two appropriate integers, non-negative integers. So you have a continuous functions from Rn to Rm. Then what you are going to do, you are going to put the appropriate Borel sigma fields on the domain side and the range side and claim that these functions are Borel measurable. So again, you get a large class of examples of Rd or Rn valued Borel measurable functions with domain some Rn. Okay, so this gives you a large class of examples. So again, this fact follows using the principle of good sets, and in particular this is using the fact that you only need to check the condition for measurability for the generating sets on the range side. If you can show that for generating sets on the range side the pre-images are on the domain side sigma field, then it is good enough to check measurability. And this part 3, which is talking about this type of continuous functions on Rn to Rm. Okay, so if you look at such functions, these are going to give a large class of examples, but then in particular we are going to look at one very specific continuous function. So fix some appropriate dimension d, look at this Rd to R function, which I am going to write it as pi I. So these are the coordinate projection maps. So what do they do? So take a vector x1 up to xd, so that's in your domain, and map it to the ith component. So ignore all the other components, map it to the ith component. So that's what pi I does. It just projects to the ith coordinate. Then this function is a continuous function. So this is a continuous function, and as discussed above, these are Borel measurable functions from Rd to R with the domain side sigma field as the Borel sigma field of Rd and the range side sigma field as the Borel sigma field of R. We are going to use these projection maps in the next lecture. So there we are going to talk about the properties of measurable functions, and we are going to need it in the next lecture. Okay, so we stop here.